Let's look at this pair of coupled differential equations. Now, one way to solve them would be to take the first differential equation and make y the subject. So we get this here, and then we just differentiate both sides with respect to time. So if we differentiate the left hand side with respect to time, we get dy dt. Differentiating e to the minus t, well, if we differentiate e to the something, we get it back, multiplied by the derivative of the power. The derivative of minus t is minus 1. Then we take the derivative of dx dt. Well, that's just the second derivative of x with respect to time. So that's what we have here. So now we can substitute into the second equation, replace dy dt with this here. So this is what we get, and if we bring over minus e to the minus t, we get 1e to the minus t added on to 3e to the minus t gives 4e to the minus t, and we end up getting this equation here, second order differential equation. So there's only one dependent variable, x. We can solve for x. Once we know x, we could go back up to this first equation here, get dx dt, and then we can solve for y. Now, instead of that approach, we can get the Laplace transforms of both equations. So let's take the Laplace transform of this top equation here. We want to get L of dx dt, where L of x, where L of little x is big X of s. And we saw in previous videos that if we get L of the derivative, we get minus little x at 0 plus x s times big X of s. This big Y is the Laplace transform of little y. So we want to get L of little y. And on the right hand side we have L of e to the minus t. Well, we can just look that up. Here it is. We set a equal to 1, so we get 1 over s plus 1. So that's what we have on the right hand side. And if we look at the second equation, we want to get L of dy dt. Well, we're saying that L of little y is big Y of s, and as we've seen before, L of dy dt is minus little y at 0 plus sy. It's just the same as this here, except we're dealing with y rather than x. And the next term is L of x. Well, we're calling that big X of little s, and on the right hand side we have L of 3e to the minus t. Well, we've already seen that, so it's 3 times 1 over 1 plus s. Sorry, 3 times 1 over s plus 1. Now the initial conditions are x of 0 equals 0 and y of 0 equals 1, so we can plug them in. X of 0 is 0, so that goes out. Y of 0 is 1, so we can bring the 1 over. So we will get 3 over s plus 1 plus 1. But adding 1 onto this is equivalent to adding s plus 1 over s plus 1 onto it. So we have 3 plus s plus 1, that gives us s plus 4 on top, with the common denominator of s plus 1. Now next we have to solve this pair of equations to find x of s and y of s. So it's simultaneous equations and two unknowns, if you like. The unknowns are big X and big Y. So we want big X and big Y in terms of little s. So one way to solve them is to use Cramer's rule. So we form a determinant from the left hand side. The determinant's entries are the coefficients of big S and big Y. So for this equation here, the coefficients are little s and plus 1. That's what we have here, s and plus 1. The coefficients of this second equation are minus 1 plus s. That's one determinant. That becomes the denominator. That's the determinant of coefficients. Now, to find big X of s, we take this determinant and we replace the x column of it, that's this column here, s minus 1, with the terms on the right hand side after the equal signs. So they are 1 over s plus 1 and s plus 4 over s plus 1. That's how we find big X of s. Now when we're finding big Y of s, the denominator will be the same as for big X of s. It's the determinant of coefficients on the left hand side. But the determinant in the numerator is got from this determinant, but we replace the y column now because we're looking for y with the terms on the right hand sides of the equations. That is 1 over s plus 1 and s plus 4 over s plus 1. So they take the place of the y column of the determinant of coefficients. So let's evaluate these. To get this determinant, we multiply 1 over s plus 1 by s, that gives us s over s plus 1, then subtract from that 1 times s plus 4 over s plus 1. In the denominator we have s times s is s squared minus plus 1 by minus 1. That's minus minus 1 or plus 1. These two fractions on top here have a common denominator of s plus 1, so we just subtract the numerators. S minus 4, that gives us minus 4 on top. And that minus 4 is divided by s plus 1, and that in turn is that fraction is divided by s squared plus 1, so we can write that as minus 4 over s squared plus 1 by s plus 1. Now we're going to use partial fractions here to get two terms whose inverse transforms we can find. So we're going to write this here as as plus b over s squared plus 1 plus c over s plus 1. Now, as we've seen before, if the denominator is a quadratic, we need a linear expression in s on top, and here the denominator is linear, so we just have a constant c. Okay, if we add these together, again we've done examples like this, we have as plus b by s plus 1. That's going to give us as squared plus as plus bs plus b. So that's as plus b times s plus 1, and then we have c times s squared plus 1. So since the numerator must equal minus 4, the s squared terms must give us 0. The s terms must give us 0, so that's a plus b. And finally the constant terms must add to give us minus 4, because that's all we have is in the numerator, a constant term. Now let's look at these two equations. Let's take this equation and subtract this equation. So we have a plus b minus c. So that gives us a minus c, and then we have 0 minus minus 4. And we add on to that a plus c equals 0, the first equation. So we get 2a equals 4, so a equals 2. We can see from the second equation that if a is 2, then b is minus 2. And if b is minus 2, then c must be minus 2 to give minus 4. Minus 2 is minus 4. So we've now found a, b, and c. So a is 2, b is minus 2. So we get 2s minus 2 over s squared plus 1. We can factorize out the 2 here. And c is minus 2, so we get plus minus 2, or minus 2 over s plus 1. Let's look at this one here. To get this determinant, we have s times s plus 4 over s plus 1 minus 1 times 1 over s plus 1. That gives us plus 1 over s plus 1. And in the denominator we have s squared minus minus 1. That's s squared plus 1. We can add these here. So we have s squared plus 4s, and then we add on the 1. That's divided by s plus 1, and the whole lot is divided by s squared plus 1. So if we do this, we get this here. We're just taking this fraction and multiplying by 1 over s squared plus 1, so we get this here. Now again, just to run through this quickly, we get the partial fractions. They have this form here, and if we add them together we have to get this. Now this time the numerator has an s squared term, so the s squared term here, as you can see, is a plus c, and that has to equal 1. The numerator has an s term, which is 4, so that's a plus b equals 4. And there's a constant term of plus 1, so that's got from b plus c. So like before, we can take this equation and subtract this equation to cancel the b's. So we've a plus b minus c, that's a minus c, equals 4 minus 1 is 3, and we can combine it with a plus c equals 1 to find out what a and c are. Okay, so if we add these together we get 2a equals 4, c's cancel, so a equals 2. If we go back up to this equation here, plug in 2 for a, we get b equals 4 minus 2, which is 2. And if we go back up here, if a is 2, we see that c is minus 1. So we have as plus b, so we have 2s plus 2. That's what we have here if we factorize out the 2 over s squared plus 1. And for c we have minus 1, so we have minus 1 over s plus 1. Now we have to invert this here, so we can write it like this. We can write this fraction as two fractions, where the common denominator is s squared plus 1, because we can easily look up the inverse transforms of these. So let's look up inverse transform of s over s squared plus 1. Well, it's got this form here with a equal to 1, so we get cos 1t. So there we have it, cos 1t. 1 over s squared plus 1 has this form here, a over s squared plus a squared with a equal to 1, so we get sine 1t, and we have the minus 2 in front. And as for this one here, we have 1 over s plus a, where a is 1, so we get e to the minus 1t. And then we have the minus 2 times that, and everything is times u of t. As for y of s, we can write it like this. We can write this fraction as two fractions. 2 times s over s squared plus 1 plus 2 times 1 over s squared plus 1. So here we have it. We've already seen these actually. 1 over s plus 1 is e to the minus t. S over s squared plus 1 is cos of t. And 1 over s squared plus 1 is sine of t. Let's take this example here. We have these two differential equations and we're given the initial conditions. Let's get L of this first equation. Let's get L of dy dt. Well, we know from a previous video that L of the derivative is given by this. Minus little y at 0 plus s times big Y of s, where big Y is the Laplace transform of little y. Then we have minus the Laplace transform of x. We'll write that as big X of s. We have to find y of t and x of t, of course. The Laplace transform of 0 is 0. By the way, the Laplace transform of 0 is not listed, but if you go back to the definition of the Laplace transform, we take e to the minus st and multiply by the function. Well, if the function is 0, we'll have 0 here. So we're integrating 0 with respect to time, which is 0. Anyway, let's go on to the second equation. With the Laplace transform of dx dt. Well, that's going to be minus x of 0 plus s times big X of s plus the Laplace transform of y, which is big Y of s, equals the Laplace transform of 1. Well, 1 is just u of t, if for positive t. That's 1 over s. And if we plug in the initial conditions, we have minus 1 here for minus y of 0, and for x of 0 we have minus 1. So we get minus 1, we get plus 1 here. Now we rearrange these equations by bringing the minus 1 in this equation over and the plus 1 in the second equation over. So for the second equation we get 1 over s minus 1. Well, we can write that as 1 over s minus s over s, which is 1 minus s over s. That's what we have here. Now I will use Cramer's rule to solve these. Let's get the determinant of coefficients. So that'll be in the denominator. So we've minus 1 s plus 1. And as for the numerator, well, we use this, but we replace the x column, which is this column here, because x appears first here, with the values with the expressions on the right hand side. That's 1 minus s over s, and the y column is the same as the y column of this determinant here. So working this out, we get 1 times 1 is 1 minus s times 1 minus s over s. Well, that's minus bracket 1 minus s, and here we have minus 1 by 1 is minus 1 minus s by s, it's minus s squared. Now let's look at y of s. Well, the denominator is the same as for x of s. As for the numerator, we have to replace the y column of the denominator with these expressions on the right hand side, and the x column remains as it is, same as the x column here. So we multiply minus 1 by this to get this. Then we have minus sign s times 1. And here we have minus 1 minus s squared. Now we can multiply this above and below by s to get s minus 1 minus s squared on top. And underneath we have minus 1 plus s squared times s. We can then take the minus sign into the top of this, so we get plus s squared minus s plus 1, and we can get partial fractions of this. So as before, we multiply as plus b by s and c by s squared plus 1. And the numerator must be equal to s squared minus s plus 1. So I'll just try and fit it in up here. We can see that the s squared term is a plus c, and that must equal 1. The s term is b, and that must equal minus 1. And finally, the constant term is c, and that must equal plus 1. So we know what b and c are. What about a? Well, if c is 1, then a must be 0. So subbing in here, we get minus 1 over s squared plus 1 over s. And we can easily get the inverse transforms of both of these terms. So let's look at this one here. Well, it's got this form s over s squared plus a squared, with a equal to 1. Don't forget we have a minus 1 in front for linearity, so we're going to get minus 1 times the inverse transform of s over s squared plus 1, where a is equal to 1, so we get cos of 1t. And over here we have 1 over s. Well, that's listed here. The inverse transform of 1 over s is u of t. We can also get it from this one. If we set a equal to 0, we get 1 over s. Then we get e to the 0 t, which is 1. So we just get u of t here. We just get rule 2 here. And as for this one here, well, that's got the form 1 over s squared plus 1. So a is equal to 1, so we get sine of 1t.